So we can look at our functions, and actually the derivative gives us an estimate for the marginal cost, marginal revenue, and marginal profit of different things. So here's a situation. You're looking at the cost of a certain product, and it's given by this function. So when I created this equation, what I was imagining is you're making something fancy. In order to make this fancy thing, you need a special machine to make it. So before you can make even your first one, you got to go out and buy this machine to make this product. And so I put a number. Even if you don't make anything, it's still going to cost you $2,000, because that's the cost of whatever machine that you're going to make. The cost of your materials come into effect, and that's what I tried to put with the 40x minus 0.02x squared. You're going to have to buy materials, but usually the more materials you buy, the better deal you get from the company. So there is a cost for your materials, but the more you buy, the less that cost is. So that's our cost function. Revenue is the amount of money you bring in. So if you are just selling things for $80, your revenue function will just be 80 times however many you sell. Revenue is important, but most companies are more concerned about profit. How much money are they actually making? Does it make sense that your profit function is how much money you bring in minus your costs? So if we do that and go 80x minus this other function, our profit function will be 40x plus 0.02x squared minus 2,000. So with that profit equation, you could figure out certain things like how many would you need to sell before you start actually making money. You could find an x-intercept that way. And you could use that to figure out a bunch of things. Now, if we wanted to find our marginal revenue, which says if we had 100 of these units and they all sold, estimate how much revenue you would make if you sold one more. Now, theoretically, we don't need any calculus for this. We always sell them for $80. So even if you've sold 100 of them, you sell one more, how much more revenue are you going to bring in? Another $80. As far as the calculus goes, if we find the derivative of our revenue function was 80x. The derivative is just 80, which makes sense, because every time you sell another one, you get another $80 to come in. Not a very exciting equation at this point, because we already knew that. But where the derivatives are more powerful is when you want to find things like your marginal cost or your marginal profit. So if we look at a derivative of our cost function, I'm trying to remember the equation off the top of my head. It was 40x minus 0.0, I'll look back, minus 0.02x squared. So it'll be 40 minus 0.04x. If you find out at 100 what that's going to be, it's going to cost you approximately $36 to make your 100th one. Your marginal profit, how much money are you then going to make from selling that 101st one? Well, if we go to our profit equation that we had from before, and if you plug in 100, which probably made sense because if the 101st one estimated is going to cost you $36, well then when you sell it for 80, your profit's going to be $44. Of course, these are just estimates. It's not a perfect answer, but it will come out to be very, very close. If you wanted to find the perfect answer, you could find how much profit you get from 100 of them by plugging 100 into your profit formula. Find out how much profit you get from 101 and plug that into your formula, and then subtract them. And that would be the actual marginal profit, the actual amount that you're going to make from selling one more. It's a lot of calculations to do that. It's a lot more numbers to work with, whereas finding the derivative and plugging in one number is much simpler to work with. And so it becomes a powerful tool as an estimate.